All right, good morning. Let's get started. We were talking about torque. So we're getting into rotational motion up until whatever it was last Thursday. We viewed every object as a point object because we didn't know how to deal with rotation yet. Every object was just a point object, and it could translate, right? That point object could move and translate. Now we're saying that not only is that object a point object, but it has some dimension to it. And because it has dimension to it, we should be able to deal with how it rotates and what causes rotation. And what causes rotation? Torque. What causes changes in translational motion? Force. What causes changes in rotational motion? Torque. And it's a little more complicated than just a force, right? It's the force and how it's being applied, where and how it's being applied to the object. So typically now when we start to draw our free body diagrams, we will draw what we call an extended free body diagram. We'll draw the shape of the object and where the forces are actually acting on it, because up until now, every object was a point object. So we could just draw a point in our free body diagram and put all the forces there. Now we have to draw the shape of the object. If it's a rod or a sphere or a box, we draw that shape and where the forces are being applied to it. Okay, let's start off with a little warm up on torque. We did some torque last time. We'll start off with this. Instead of ranking these, let's actually calculate the torque in each case. So this is a meter stick. So it's 1 meter long, and that weight is 1 kilogram. Okay, so let's find the torque in each case. Let's do E first. We'll do E first. There's my free body diagram. Torque is force times lever arm, right? And if we extend the line of force, find that perpendicular distance to the axis of rotation, that's our lever arm. So what do we get in this case? We get mg times the lever arm. M was 1. G, I'm just going to use 10. And D is 1, right? And our units for torque, Newton meters. If you work on your own car, you might own a torque wrench. So the torque wrench is set, so a lot of the nuts and bolts on your car, they spec how much torque you should have, like on the tires, the lug bolts on the tires, they spec how much torque you should use to tighten them. You don't want to over tighten them. You don't want them too loose. So you can buy a torque wrench, and as soon as you set it to the right torque, and as soon as you apply the right amount of torque, it clicks, and you know you can stop there. You don't have to push anymore. So those are, sometimes they're in Newton meters, but a lot of them in the United States are in foot pounds or inch pounds, things like that, the imperial units. Okay, let's do B. We'll work our way up to the more interesting ones. Okay. What am I forgetting here? What should I be including for a complete answer? Direction. Torque is a vector quantity, so I should be including direction also. So let's think about this for a second. We do have a way to pick direction. Let me right. So let me do this. Let me get my bicycle wheel. There we go. Can we see that? Back a little bit. I'm going to stop sharing my screen for a second. There we go. Okay, here's my wheel. So if I give it a spin, I can spin the wheel like this, right? And we know that quantities like velocity and acceleration have direction associated with them. Torque is a vector quantity. It has a direction associated with it also. So if I get this wheel spinning, it's got some angular velocity. What direction would you use to describe that? A lot of you might say clockwise, right? Does that work? If you said clockwise, what would I say? I'd say, no, you're wrong. It's going counterclockwise. I can see it. It's going this way. It's counterclockwise. So clockwise and counterclockwise depends on the location of the observer, right? If I'm standing on the front side like you are looking at it, it looks like it's clockwise. If I move around to the back and look at it, it looks like it's counterclockwise. So we need something we can all agree on. And what do we do in physics when we want to define a plane? We pick a vector that's normal to the plane we want to define, right? Because in the plane that we're looking to define, there are an infinite number of vectors. But if we pick one that's normal to the surface, that kind of defines the plane. And it's the same with rotation. What we'll do is we'll pick a vector that points along the axis of rotation. And we'll use our right hand to figure out the direction. So if this is spinning like this, I'm going to wrap my right hand, my fingers around. I'm going to put my thumb along the axis of rotation. And I need to figure out which way do I put my thumb along the axis of rotation points from me to you or you to me, right, along the axis of the wheel. So I need to put my thumb either pointing toward you or pointing toward me. That's the question. Which way is it? Well, if it goes this way, I want my fingers on my right hand to wrap in the direction the wheel is turning when my thumb is in the axis, along the axis of rotation. If it was spinning this way, I'd stick my thumb pointing toward you and my fingers would wrap around in the direction the wheel's rotating. So we can all agree now. I'm standing on this side of the wheel. You're looking from the other side of the wheel. But if I spin it like this, we can all agree the angular velocity points toward me. And if I spin it like this, we all agree using our right hand rule that the angular velocity points toward you. Okay. So it's similar with torque. Torque points along the axis of rotation. And we would just wrap our fingers in the direction the torque would cause this thing to rotate. So if I have a rigid object like this, and I hang a weight over here at this side, pulling down, I hang a weight right here, and that weight is going to pull down right here and produce some torque, pulls on the wheel right here, down, produces torque that would cause the wheel to spin this way. So the torque points toward you. If I hang the weight over here on this side, so it pulls down, causes the wheel to spin this way, I need my right hand back. Always use your right hand. I wrap my fingers in the direction the wheel would turn because of the torque, and the torque would point toward me. So the torque, in this case, the torque points into or out of the page because the torque is within the confines of the page, right? All right, so for E, this object would rotate, as we look down on the page, would rotate clockwise because of that torque. So I'm going to take my fingers and roll them in the clockwise direction. My thumb is going to point along the axis of rotation for sure. The question is it along the axis of rotation is perpendicular to the page? So the question is does my thumb point into the page or out of the page to determine the direction of the torque? Well, I wrap my fingers in the direction this rod would go if that weight was hanging on it, and it would go clockwise. So my thumb points into the page. Oops. And this next one is also into the page. Okay. Let's do A. The direction is the way your thumb points. Yeah, so for torque, you put your thumb along the axis of rotation. So you have a 50-50 chance of getting it right. And then you orient it such that your fingers roll in the direction that the object would turn due to that torque. So we're doing A now. How are we doing on this one? Okay. Let's do C. Oh, is it 8.7? Oh, you're right. Sorry. 10 times 0.87. There we go. Thank you. And C, we have like that, right? You extend the line of force. Find that perpendicular distance. That's D. So this is the exact same as the last one. Okay. You can do the last one on your own, right? Now, I don't know why physics textbooks do this, but they seem to always define positive theta as counterclockwise. When you do kinematics, they tell you to pick any direction you want to be positive, right? And pick what makes sense for the problem. If up makes sense, pick up as positive. If down makes sense, pick down as positive, right? Whatever you want, it works. Just be consistent and get the right answer. But for rotational motion, they all like to go with sort of the math convention for how we measure angles, and that is you start on the positive x-axis and move counterclockwise to get a positive angle. I say use whatever direction you want to be positive. if clockwise makes sense, call clockwise positive. If counterclockwise makes sense, call counterclockwise positive. Just be consistent and get the right answer, just like we did when we did linear motion. But if you're looking up answers in the back of the book, that's by default, they almost always use counterclockwise as positive for theta and omega and alpha, and clockwise as positive. As counterclockwise is positive, clockwise is negative. So we already said we use the right hand rule, right? And omega and alpha point along the axis of rotation. Okay, so there's a couple of ways that we can sort of talk ourselves into understanding what the rotational inertia is. We want to think about rotational inertia now. One is with kinetic energy, and the other one is with Newton's second law. So let's take a look at Newton's second law here. And in special cases, when the torque, when the force is perpendicular to the radius where we're applying something, the torque is just the force times the distance. And we know that A is equal to R alpha, right? That's how we can translate back and forth between translational, how we can convert back and forth between translational motion and rotational motion. We multiply by the radius, right? So using these, what we get is torque is our F. F is MA. A is R alpha. And so we get torque is M R squared alpha. And if we add it all up, the net torque is the sum of the right side, but alpha is the same for every point on an object, right? If something's rotating, every point on that object rotates with the same angular speed and the same angular acceleration. So I can pull it out of the sum. And we compare this to F equals ma. If we compare this to our F equals ma equation, we say that we have this, instead of a net force, we're going to use a net torque acting on the system. And instead of saying that that causes changes in acceleration in a translational sense, we're going to say it causes changes in an angular acceleration, alpha. And if we do that, then what's the proportionality constant between net force and acceleration? It's the inertia, right? Mass, inertia. So what's the proportionality constant between net torque and angular acceleration, alpha? It's probably the angular or rotational inertia. So these two things should line up, should be the same thing. One is the translational inertia, one is the rotational. Okay. So this is for point objects. This is for point objects. Let's talk about it a minute. So first thing we have is for a point object. We use capital I for rotational inertia. And we already said it's not just the mass anymore. It's the mass, it's where the mass is located with respect to the axis of rotation. R is the distance from the axis of rotation to where our mass is, and we multiply it mr squared to get the rotational inertia. But we can have multiple point objects, right? We can have more than one object in our system, and we might want to know what the total rotational inertia is. Just like when you would pull your wagon, you might have more than one object, and you might have a basketball in there, you might have a friend sitting in the wagon, you might have a brick in there, whatever. You might have a bunch of stuff in your wagon. Well, how do you get the total inertia of the wagon? You add it all up, right? The mass of each one of those things added together is the total mass. We do the same thing with rotational inertia. We just add up the individual rotational inertias for all the objects in our system. So for multiple point objects, we add them up. And what's the next thing we're going to do? We sometimes we don't have point objects. Sometimes we have solid objects, right? Rods and discs and wheels and spheres. So for solid objects, what happens to that summation sign? It turns into an integral. So we pick, what do we do in physics when we want to think about what happens to a solid? We pick a little tiny infinitesimal chunk of the solid, little tiny part of the total mass. We call that dm, little tiny chunk. And because that chunk is so tiny, we treat it like a point object. And we say, we multiply it by r squared, and we sum up all the contributions from all the little dm's. And that's an integral. So we saw dm when we did center of mass. We learned how to integrate over it, convert that into something we can integrate over, and we're going to use it again now to find inertia of our solid objects. Okay. Let's do this one, I guess, since it's here. Let's just find the torque. Let's not worry about ranking them. Let's just find the torque for one of these. How about for A? Okay, so you're finding the torque that hanging mass is producing on that disk. You can use 10 for G. Is that what you're asking? If we extend the line of force, what's the lever arm? The radius, right? So in this case, what do we get? The force is m times g. M is half a kilogram, right? G, I'll just use 10. And the dis is 10 centimeters is 0.1 meters, right? So half a Newton meter. We all on the same page? Because we are, question is, which mass do we use? The mass of the disk or the hanging mass? We are interested in the torque right now, right? The torque. What's causing the torque? Some weight hanging off the radius of this disk. The disk has nothing to do. The disk is not producing any torque on itself, right? Because it's uniform and the pivot point is at the center of the disk. Okay. So we are concerned with the hanging mass. Good. All right, you can do the others later. They're the same. Let's move on. We'll do this one. But what we'll do, actually, let's rank them. What should we do? Should we rank them first or? Let's find I in terms of D and M, where each one of these has mass M. And this spacing is D. Okay, spacing is D, mass is M. So these masses, these little point masses are connected by some kind of massless rods. And we want to know, it's going to rotate this grid of masses is going to rotate about this axis of rotation right here. Okay, that heavy line right there, that axis of rotation. So let's do it for A. Oh, sorry, I missed the question. On the last one, yes, I use the lowercase d is the lever arm. The lever arm. And in this case, the lever arm is the radius, not the diameter, is the radius of the disk. And in almost every case where you have a disk, it's the radius of the disk. Why is that? Because that string, when a string comes off of a pulley or a wheel or a disk, it always comes off tangent to the wheel or the pulley or the disk. And that means that the lever arm is going to be the radius of the disk. Okay, thanks. So I'm going to number these. I'm going to number them 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we're only going to do A right now. It's the same technique for all of them. So what's our situation here? Multiple point masses. Where's our... So multiple point masses. What are we going to do? We're going to add up, just take m times r squared for each individual one and add them all up. Okay, so I'm just going to, they all have the same mass, so we'll just use m. m1 is just equal to m. And what is its distance to the axis of rotation? Zero. It is right on the axis of rotation. So it doesn't contribute anything to the rotational inertia of this object. It doesn't make it harder to rotate. It doesn't prevent it from rotating, right? It's right at the axis of rotation. It's zero. And m2 is m times zero. And m3, same thing. So this is m1. Or I guess I should call it I1. Let's call it I1. Okay, let's do the next three. M4 times what? Yeah, the d squared. The distance is d. We're looking for the distance from the axis of rotation to our mass. So it's just a distance d. So this is going to be m times d squared for object, that's the I, the rotational inertia for object 4. And 5 is going to be the same. And 6 is going to be the same. You see that? 4, 5, and 6 are all have the same position relative to the axis of rotation, the same distance from the axis of rotation. So they all contribute the same amount to the rotational inertia of this object. Now let's do 7. This is going to be 2D, right? 7 is 2D away from the axis of rotation. And we're going to square that, square the distance to the axis of rotation. So it's 2D quantity squared. Same for 8 and 9. And we have one more. M10 is 3D away from the axis of rotation. You see that? This distance. (3D). So we can put that in over here. And this is I for mass 10. And we do the math. I get 24 md squared. Okay, you can do the others later. But what I would like to do, without calculating anything, just look at these and rank them. Which one do you think has the largest rotational inertia? Which one do you think has the smallest rotational inertia? Just go through and rank them. Sometimes it's easiest to see the extremes. So C is going to be the largest one. We see that? It's got 3 masses. Look at that. 3 of them that are 3 away. That contributes a lot, a lot to the rotational inertia. D doesn't have any. B and D don't have any that are 3 away. And in B, one of them is in close. How do you get from B to D? You move that out. So that's going to increase. D has to have more rotational inertia than B because the mass is a little farther out. So if we rank these, what do we get? C is the biggest. B is the smallest. Is that what we said? A and D are in between. And this is what I got. You can, if you want to do it later, you can check your answers. For C, I got 37. And for D, I got 16. Does that match with our ranking? B is the smallest, then D, then A, then C. Yeah. Okay, seems to work. Okay, let's take a 10-minute break. I'll pause the recording. We'll start up again in 10 minutes. All right. Let's do this. Let's take a look at this object. We've got a 3 meter by 2 meter rectangle over here on the right side, and 3 forces, F1, F2, and F3 being applied to it. They're all equal magnitude, but they're being applied at different angles and locations to this object. Think of it like a big board or something, big flat solid object. So there's 3 possible axes of rotation, A, B, and C. They are all perpendicular to the page, right? So we've got our object here like this, our 3 meter by 2 meter object. We've got an axis of rotation that's perpendicular to the page at location A is one corner of the disk. So it can rotate, right, about that axis of rotation. Looking down on the page looks like this, right? C is more in the middle, right? C is like that. So it rotates on this, if C is the axis of rotation. Okay, we got it? So A says, is the torque caused by F1 about point A, clockwise, counterclockwise, or 0? So it's a little easier to see this one. There, is that better? The torque caused by F1 about A is clockwise. We okay with that? So again, think about this. If this is the sheet, and A is this, the axis of rotation is this upper corner here, so it's free to rotate about that axis of rotation. F1 is pulling at an angle down here, causing it to go. Well, I guess F1 is really over here, right? A is in this corner, looking down on the page, right? And then F1 is pulling down like this, causing it to go clockwise. Did I get that right in the camera? So if you gave this a tug right here, this whole board would swing in that direction. Okay, it says B is the torque from F1 about point B, clockwise, counterclockwise, or 0? Clockwise. Same situation as the other one, right? How about C? C says, is the torque produced by F1 about axis of rotation C, clockwise, counterclockwise, or 0? If you extend the line of force, it goes right through that axis of rotation. There's 0 lever arm. It cannot cause it to rotate. Right? Think about, just look at that. If you're pulled at that location, that board is not going to rotate because your force goes right through the axis of rotation. All right, same questions for the next one. F2. What direction is the torque about axis of rotation A from F2? It is 0. Again, you extend the line of force, and it goes right through that axis of rotation. You can't make it rotate by pushing that way. And what else is going to be 0 looking at this diagram? The torque about axis C is also going to be 0. That's, which one is that? F here. F2 about axis C is going to be 0. How about B? If you push on this thing with that force F2 and the axis of rotation is B, does this thing rotate counterclockwise or clockwise? Counterclockwise. That way. Last one is F3, about axis of rotation A. Counterclockwise. And about axis B. And C. They are 0, right? You see that? One way to see that is you've got your object here. So my hand will be axis of rotation B, right? So this is free to rotate about axis of rotation B. And my other hand is the force, F3, pulling over here, right? So if I pull, I can't get it to rotate there. But if I pull down here, as I pull, it starts to rotate right away, right? But if I pull here, it doesn't rotate because my line of force goes right through the axis of rotation. If you're having trouble seeing these, just get a piece of paper, hold it with your finger at where it says A, one corner there, and pull on it in the other places and see what happens, right? You should see it rotate or not rotate. All right, let's do this. Let's find the torque from force F1 we're going to find the net torque is what we're going to do about each axis of rotation. So what I think is easiest is let's think about one force at a time and look at how the torque it produces about each axis of rotation. Then we'll go to the next force. Okay, so this will be the torque from F1 about A, B, and C. So what is the torque produced from F1 about axis of rotation A? And we're using, what are we using? We'll just, we'll call, I think it said this was 1 meter, right? It was a 3 meter by 2 meter grid, right? So the spacing is 1 meter and the magnitudes are all the same. We'll just call it F. So we can extend the line of force, right? Oh, I didn't want to do it here. I wanted to do it down here. And we find the perpendicular distance from that line of force to A. So I'm going to call that dA. So what do we get here? The torque is F1 dA, which is equal to F times the square root of 2 times 1 meter, right? Which is equal to F times the square root of 2. We good with that? The diagonal of a square is the square root of 2 times the length of the side, right? How about if we look at the torque that F1 produces about axis of rotation B? It's going to be the force times, yes, we do. Good question. Let's finish this first. Let's get the magnitudes here first. But good question. The question is, don't we need to define a direction here? Torque is a vector quantity. So axis of rotation, I'll use green, I guess, for the next one. I'll call that D, the lever arm for axis of rotation B, D sub B. So what do we get? We get the force times the square root of 2 over 2 times 1 meter, which is just F root 2 over 2. What happened? And for axis of rotation C, we get 0. The line of force passes right through axis of rotation C. There's 0 lever arm. It cannot produce rotation about that axis of rotation. Just use your trig functions. It's a 45-degree angle, right? You're trying to find the diagonal of a square is 45, is the square root of 2 times the length of the side. So if the length of the side is A, right, Pythagorean theorem tells you that, what am I calling it? Capital D. Capital D squared is A squared plus A squared, right? So D is the square root of that. Okay, we're good here, right? You can also break each one of these into components. Yeah, that works. Yes, it does. So, okay, so let's define a direction. What do we want to be positive, out of the page or into the page? How about out of the page is positive? So F1 acting on this object, what does the torque about axis A want to do to it? Cause it to go clockwise or counterclockwise? F1 about axis A would cause it to go clockwise, right? Yeah, I have confirmation. So we're saying, remember, you wrap your fingers. If your fingers are going clockwise and your thumb is along the axis of rotation, which is perpendicular to the page, your thumb would have to be pointing into the page for your fingers to be going clockwise. So this is into the page or negative. So our torque should be negative F times the square root of 2. Let's do this. Let's say I don't have a lot of room here, but I'm gonna do this. I'm gonna put magnitude of the torque is equal to, and then down here, I guess I should have a torque. Let me see if I can squeeze it in. Torque with the vector minus F times the square root of 2. There. And magnitude of the torque equals. So if the torque acts, F1 acting on this object about axis B would also cause clockwise rotation. So that would be into the page. We okay with that? Same as the other one. And this one is 0. Okay. Ready for the next one? Now we want to do torque from F2 about A, B, C. A and C are 0. And B, you have this lever arm right here. So you get F square root of 2 over 2. And is it positive or negative? Positive, right? It is out of the page. Or positive. And one more. And this one is also positive, is that right? All right, so let's find the net torque. For axis A. That's going to be the torque from F1. Vector addition. And we said, what did we say? Out of the page was positive, right? So we got a negative. Let me just check here. Yeah, negative F root 2. 0 and what am I looking for? Yeah, and a positive F. I'm looking at the first column, right? Axis A, right? Only care about this column. So F1 about axis A, negative F root 2, F2, 0, and F3, F. All right. Follow me? We just add them up, vector addition. So if they point up, if they all point up, you just add them up. If they all point down, you add them up. If they point in opposite directions, you have to subtract, right? One from the other. They cancel a little bit. So now we're finding the torque about axis of rotation B due to F1, F2, and F3. And I get a negative F root 2 over 2, positive F root 2 over 2, and 0. So there's no net torque about axis of rotation B. So if it wasn't rotating, it's not going to start rotating. Okay, I'm not sure if you spotted that when you just looked at this thing, but F3, of course, we spotted that F3 wasn't going to produce any torque, but F1 and F2, it turns out they cancel. F1 is pulling this way, F2 is pushing that way, and those two exactly cancel out about axis of rotation B. And the last one, axis of rotation C. The torque due to F1. Adding up all the contributions, I get 0, no torque. Okay. Play with those a little bit at home. Make sure you understand them. I want to talk about kinetic energy. Let's take a simple object. Let's take 4 point masses, and we'll connect them with massless rods. Okay, so we have a rigid object, but we're just going to treat it like 4 point objects. So I've got okay, these are massless rods, and this is our axis of rotation. Axis of rotation perpendicular to the plane of the page, and these are going to start rotating. And if this thing is rotating, we want to know what's the kinetic energy of the system, of this rotating system. Well, we've got 4 masses that are moving. So the kinetic energy of the system is going to be the kinetic energy of each of these masses added together, right? We've got the kinetic energy of this rotating system is the kinetic energy of mass 1 plus the kinetic energy of 2 plus the kinetic energy of 3 plus the kinetic energy of mass 4. These are the translational kinetic energies, right? We're just going to treat them at any instant in time. We can say this mass is moving with velocity v, even though we know it's rotating. We can say it's moving with velocity v, and its kinetic energy is 1/2 mv squared. So we'll write that in here for each one of these. 1/2 m1 v1 squared, 1/2 m2 v2 squared, and we keep going. Oops, that's a 4. Looks good to me. The whole system is rotating together, yes. So they have the same angular velocity, the same omega, but their translational velocities will be different. Because they're different distances from the axis of rotation. Remember, how do you translate, how do you get from rotational velocity to translational velocity? You use V equals R omega. So on a rigid object, every point on a rigid object has to complete one revolution in the same amount of time. So every point on a rigid object that's rotating, doesn't matter if it's this object here, or rotating about the center point, or over here, every point has the same omega. But a point way out here, if it's rotating, if this is my axis of rotation, a point out here has to have a faster translational speed than a point closer to the axis of rotation. So V, translational velocity, equals R omega. All right, we're going to use V equals R omega. I've got 1/2 m R omega squared, 1/2 m. It's a good thing I only have 4 of them, right? And what did we just say? We just said that every point on a rigid object has the same omega. So omegas are all the same. That means I can rewrite this as 1/2 the sum of m r squared times omega. This is our rotational kinetic energy. Now, what have we always used for kinetic energy? Thank you. Omega squared, yes, thank you. What have we always used? We've used 1/2 m v squared. So instead of v, we have our rotational counterpart, right? Omega. And instead of m, our inertia that we've been using for translational motion, we need some kind of rotational inertia. We already showed that it was mr squared, but this is sort of a second way of showing it. This must be our rotational inertia. This is for point masses. So in general, we can say for any object that's rotating, its kinetic energy is 1/2 I omega squared. So we could go in, if it's point objects, we could go in and calculate it from translational kinetic energies and add them up. But that becomes more difficult when it becomes a solid object that's rotating. But we have a formula here that works for either case. We can just treat it like an object that's rotating and use 1/2 I omega squared. Okay, let's calculate I. Let's calculate I for the rotational inertia. I for a thin uniform rod rotating about its endpoint. There's our axis of rotation. Okay, what is our formula? The integral of r squared dm. First thing you want to do, pick some little arbitrary chunk. Don't pick a point at the very end. Don't pick a point at some special place. Some arbitrary little chunk of mass. Call that dm. And where is it located? It's located a distance x from the axis, and it has a thickness, a width of dx. Now, what is r? R is the distance from dm to the axis of rotation. So if you put the origin at the axis of rotation, it's x, like I did in this case. And dm, remember, is lambda dx. Lambda is our density, mass density. And if it's uniform, that's just the total mass. Well, we'll get there. Well, I guess I should have told you up here. Let's say total mass m, total length L. Okay, are we ready to integrate? So I is the integral of r squared dm. R is x, we said. dm is m over L dx. And what are we integrating from? We're adding up every little element of mass, dm, every little tiny element of mass in the whole rod. So we're integrating from one end of the rod to the other. And this rod is located between 0 and L. We're integrating from 0 to L. One third ml squared. Now it's going to change. This is only for a uniform rod rotating about its end point. If we rotate the rod about its center point, what happens to the rotational inertia? It will change. More or less. Did you do the integral? If we're finding it about the center point, let's do it. But before we do it, you should be able to just look at this and tell me it's going to be more or less. Which one is going to have the bigger rotational inertia? Where's my, I need a, here, I've got a rod here. I'm going to hold it in the center and I'm going to twist it. Now I'm going to hold it at the end and I'm going to twist it. One of them feels very different than the other one. One of them is much harder to rotate and harder to stop rotating. One of them is much easier to start rotating and stop rotating. The axis at the end has to be much greater, right? Much greater. Because what did I do here? Here I have half of my mass in close to my hand, and the other half is also in close. But if I take this half and I move it way out here, then I have this situation. I've moved half the mass way out, and I'm multiplying each one of those by r squared. This is a much bigger rotational inertia than this one is, okay? Next time we will do this, but you should do the integral and see what you get. Set it up, do it, see what you get. You get a much smaller number. Okay, we'll keep moving through this material. We have only 2 weeks between the last exam and the next exam, right? So a week from Friday, a week and a half from now, is the next exam. That's at the end of week 9. We only have 10 weeks in this quarter. So there'll be an exam on that Friday. I forgot the date. Then there's 1 more week of classes where we'll cover some new material. And then we have our final exam the week after that. So take a look at the calendar, stay on top of things, finish strong. Just a little ways to go here. So finish strong. And let's see, I'll stick around. I'll stop the recording, but I'll stick around if there are any questions. And if you can't stick around, then there's always office hours. All right, I'll stop the recording.